In June 2025, a car carrier ship caught fire suddenly in the Pacific Ocean. The ship was carrying 3,000 cars, about 800 of which were electric vehicles. The fire initially broke out on the deck loaded with electric vehicles. Ships have their own firefighting systems, but as you know, traditional firefighting methods are useless against lithium battery thermal runaway. Eventually, the crew had to abandon the ship to save their lives, and the ship sank. This accident is a real milestone. In 2025, China exported over 2.6 million new energy vehicles, so shipping them overseas will certainly be the norm for China's automotive industry in the future. Although the safety of power batteries is visibly improving, theoretically, they are still more prone to catching fire compared to traditional fuel cars. This renders previous ship firefighting design experiences ineffective, necessitating specialized tools like fire simulation and surrogate model. Let's start with fire simulation. Simply put, fire simulation is like starting a fire in the digital world. It calculates how the fire evolves, providing reference for firefighting design and subsequent extinguishing plans. From the underlying logic, traditional fire simulation is essentially computational fluid dynamics, CFD, a branch of it. But beyond standard CFD, many additional factors need to be considered. For instance, chemical reactions need to be simulated for the combustion process, such as thermal radiation, because in a fire, a lot of heat is transferred through thermal radiation. Then there's smoke transmission, tracking the spread of toxic substances like carbon monoxide and smoke. You understand the theory, but in practice, whether using general CFD software or specialized fire simulation software, when facing the complex structure and large space of a car carrier ship, along with thousands of potential fire sources, efficiency becomes a major issue. For example, let's assume there are 8,000 cars on the ship, each of which is a potential ignition point, and they are particularly dispersed. If you use simulation software to calculate every fire source location, different fire source power, and different fire door openings, the workload would be overwhelming. You'd certainly be running away overnight in a panic. It's not only troublesome, but also very slow in computation. Now imagine the fire is already raging and firefighters are desperately waiting for you to come up with an extinguishing plan. But then you tell them to wait for about 2 hours for the iteration to converge, which delays the response. Thus, surrogate models came into existence. The core idea of surrogate models is to use a small amount of high-precision simulation data to train a small model, allowing it to learn the pattern between fire inputs and outputs. In the future, when faced with new fires, the small model can quickly provide simulation results. There's no need to solve complex fluid equations anymore. As a high-tech company proficient in industrial AI and CAE simulation, Tianfu recently used surrogate models to conduct fire simulations for a shipyard, achieving excellent results. Before training, CFD fire simulation software is used to calculate 150 fire scenarios to generate input data needed for the surrogate model. Then this data is used to train with a deep convolutional neural network, generating the surrogate model. Finally, when facing new fire scenarios, calculations are done using both the surrogate model and CFD software. The results of the two calculations turned out to be almost identical, but the surrogate model only took a few hundredths or even a few thousandths of the time compared to CFD. It comes out in a flash. Combining high-precision CFD with efficient surrogate models like this, it makes complex ship firefighting design achievable, and I want it all. In the future, when facing fires on transport ships, firefighters can get response plans in the shortest time. They might no longer need to abandon the ship to save their lives.